Good morning, good afternoon, or good evening, depending upon where you are in the world, and welcome to today's webinar, High-Speed Data Acquisition Using Analog Devices DAC2 and Intel's Aria 10, brought to you by Tech Online, Arrow, and Analog Devices, and broadcast by AspenCore. I'm Chris Keach, and I'll be your moderator today. We have just a few brief announcements before we begin. First, the slides will advance automatically throughout the event. You may also download a copy of the slides by clicking on the green folder icon located at the bottom of your screen. You can also participate in our Q&A session by asking questions at any time during this webinar. Just type your question into the Q&A text area located to the right of the presentation window and then click the Submit button. Please note that we'll try to get to as many questions as we can with the time that we have left at the end of today's webinar, but if we're not able to get to your question today, someone will be getting back to you via email after the program is over. Also at this time, we recommend that you disable your computer's pop-up blockers. This will allow the slides to advance automatically throughout the event. And at the end of the webinar, we will ask you to complete our feedback form. Your feedback will provide us with valuable information on how we can improve future events. You can also launch the survey at any time by clicking on the red survey button at the bottom of your console. And if you're experiencing any technical problems, please type your issue into the Q&A text area, and we will be glad to offer one-on-one assistance. And now, on to the presentation. High-speed data acquisition using analog devices DAC2 and Intel's Aria 10. It's my great pleasure to introduce today's presenters. Our first speaker is Peter Bello, Applications Engineer, Engineering Solutions Center, Arrow Electronics, and Stephen Kravatsky, Principal Applications Engineer, Engineering Solutions Center, Arrow Electronics. Joining them is Robin Getz, Engineering Director, Systems Development Group at Analog Devices, and Lars-Peter Clausen, Systems Architect, Systems Development Group, Analog Devices. It's with great pleasure I now turn this special session over to Peter to begin. Peter?
Thanks, Chris. Welcome, everybody. Here's the agenda for today's webinar. We've broken this into two parts. In part one, we will discuss the JESD204B interface, why it is important, which applications benefit the most from it, and an important feature called deterministic latency. We will then look at the interface framework that has been developed for it and how the individual parts work together. Part two is all about the new high-speed data acquisition kit from Arrow. We'll cover what's included in the kit along with a brief description of the major components. We will look at how to set up the kit to run the built-in demo, including where to go for all documentation, firmware, and software. We'll examine the path the signals take as they travel from the Aria 10 FPGA across the JESD204B interface to the analog devices data converters and back. We'll show you how to input different waveforms and view the outputs on your PC using Analog Devices IIO oscilloscope application. Then we will look at how to use this kit to develop your own products. At the end of the presentation is a list of resources in case you want more information. Before we get into the particulars of the kit, let's take a look at why we need it. What is JESD204B and what was it designed for? JESD204B is a high-speed serial interface designed to move data between logic devices, such as FPGAs or ASICs, and data converters. It does this using either printed circuit board traces, a backplane, or one or more cables. The maximum distance between transmitter and receiver is specified as being no more than 8 inches. It is point-to-point between a single transmitter and a single receiver per link, as opposed to a bus standard. Multiple data converters can interface with a single logic device over a single link if the data converters are all on the same IC. Additionally, multiple data converters on multiple ICs can interface with the FPGA using multiple links. The JESD204B standard specifies 12.5 gigabits per second per lane with multiple lanes allowed, up to 32. Note that there are devices out there already which exceed this rate. However, this is what the current standard specifies. So why do we need this? The main reason is to reduce the overall solution size as well as complexity from a hardware standpoint. Up until JESD204, designers used parallel interfaces such as CMOS and LVDS to move data between logic devices and data converters. These require a separate pin on the IC for each bit of resolution. A 16-bit DAC, for example, needs 16 pins just for the data. For an 8-channel 16-bit DAC, this would require over 100 pins just for the samples. More package pins also meant more PC board traces, resulting in a multi-layer board. On top of that, the board traces had to be matched in length for equal propagation delays, so the data will all arrive at the same time. This increases the board size even further. The solution was the invention of JESD204 and subsequent revisions 204A and B. Since this is a serial interface, fewer package pins are needed, resulting in a smaller package, and fewer board traces are required. In addition, traces no longer have to be matched in length, as the clock phase information is embedded in the serial data stream. This all results in a smaller PC board that is also easier to lay out, and a smaller solution results in a lower BOM cost. There are, of course, trade-offs when switching from parallel CMOS or LVDS to JESD204B. The software complexity goes up. This is due not only to the serializing of the data, but also the embedded timing elements. Also, since this is a serial interface, overall latency, the time it takes for the data to propagate from input to output, increases versus the parallel format. So where is this used? Applications that have a lot of data converters, applications requiring high sample rates, 1 gigasample per second, for example, and applications requiring real-time, on-the-fly configurability. Some examples are shown here: cell towers, software-defined radio, medical imaging, radar, and secure communications. An important feature of JESD204B is deterministic latency. As shown in the diagram, for JESD204B, this describes the time it takes for the signal to propagate from the input of the transmitter across the serial interface link to the output of the receiver. And it is a fixed and known amount of time from one power cycle to the next. So why is that important? Certain applications, such as MRI machines, need to be able to synchronize a large number of data converters, have all the data arrive simultaneously. Other applications, such as military defense systems, require that the overall latency be below a certain value so the system can respond quickly. The way JESD204B achieves deterministic latency is basically due to 3 elements. Number 1, each lane has alignment characters added into the serial data stream. Number 2, there's a buffer on the receiving end which keys off these characters and holds all of the data until the lanes have all arrived. And number 3, there's a master timing signal, which for subclass 1 devices is called sysref, which instructs the buffer to release the time-aligned data on a specific clock cycle. Now I'm going to hand control over to Lars.
Thanks, Peter, and hello, everybody. In this next section, we will talk about the analog devices JESD204 interface framework. This is a fully integrated framework covering components from multiple categories. Integrated in this case means that all the components that are part of the framework have been co-designed with a special focus on interoperability. As you've seen earlier, a JESD204 converter system is made up of many different components, and you can see a schematic overview of such a system again on the right side. You've got the converter doing the A to D or the D to A conversion, the FPGA doing signal processing, and the clock chip providing all the system clocks. And rather than treating them as independent individual components, the frameworks provide a unified view to interface with them. At the hardware level, the framework provides rapid prototyping systems like the AD, FNC, DAQ2, EBZ that will be introduced later in this presentation. At the gateway level, the framework provides all the HDL components that are necessary for JESD204 protocol handling. And at the software level, the framework provides drivers to configure sample converters, clock chip, and other hardware components, as well as the gateway HDL component. Also available are auxiliary software components for capturing and analyzing data. The JESD204 interface framework is used to implement the demo that will be presented later in this presentation. Some of the key features of the framework include automatic interface configuration based on application configuration, dynamic link reconfiguration at runtime, as well as improved diagnostics. We will look at each of these on the following slides. One of the key benefits of the JESD204 interface framework is that it hides the details of having to manually initialize the JESD204 link. When setting up a JESD204 link, it is necessary to correctly configure all components involved on the link, and this typically involves performing register writes with the appropriate values. The JESD204 interface framework distinguishes between interface and application configuration parameters. Application configuration parameter settings are performance differentiating factors like, for example, the sample rate, number of enabled ADCs, or whether signal processing is performed or not. Interface configuration parameter settings, on the other hand, are concerned with the setup of the data link that is used to transport sample data from the converter to the application logic where they can be used. This, for example, can be the lane rate, the number of lanes that are used, or the specific reference clock for the high-speed transceivers. In a sense, interface configuration parameters are a necessary evil that are required to be programmed to get the data of interest from A to B, but they're not very interesting on their own. Interface configuration settings often directly follow from the application configuration settings. For example, increasing the sample rate needs a corresponding change in the lane rate, or a change in the number of lanes used. As such, the JESD204 interface framework is able to automatically compute those interface settings for a specific set of configuration settings. For example, there is often a limit on the minimum and maximum lane rate, which can be different from device to device, and the framework might choose to dynamically enable or disable lanes to make sure that the lane rate is within the limits required by all devices on the link. This allows the user to focus on developing the application rather than having to care too much about the low-level details of the JESD204 protocol or how the sample data is transferred from the converter to the application. Having the capability to automatically derive and program interface configuration settings makes it also very easy to support dynamic reconfiguration in runtime. For example, it is possible to change the sampling rate from, let's say, 250 megasamples to 1 gigasamples by calling the appropriate API function. One major issue when setting up or designing a new JESD204 converter system can be figuring out why things are not working when they are not working. Hardware component or layout issues or misconfiguration of any of the many configuration parameters can cause the JESD link to fail completely or to produce only garbled and incorrect data. Having to manually identify the source of the problem can be a long, tedious and difficult task. Or maybe there are even multiple problem sources, in which case this can become especially difficult. This is why the JESD204 interface framework provides many introspection points and other diagnostic capabilities. These allow a step-by-step analysis to narrow down the source of the issue. On the right side of the slide, you can see a few example diagnostic outputs. Among the diagnostics offered is test pattern monitoring. This helps to identify electrical signaling issues. If, for example, there's a lot of noise or too much attenuation in the PCB traces, the bit error rate goes up, more bits are going to randomly flip from ones to zeros or vice versa. This can significantly affect the quality of the captured or transmitted signal. Test pattern monitoring, where known data sequence is being transmitted, allows to quantify the quality of the link. The receiver will be able to compare the received data to the expected data and compute the average bit error rate from this. Clock monitoring is available for all major system clocks. This helps to ensure that each clock is running at the required clock rate and also allows to detect if a clock is not supplied at all, for example due to bad wiring. During link startup, the transmitter also sends a so-called initial lane alignment sequence. It contains, among other things, a unique lane identifier which can be used to ensure that lanes are connected correctly and not accidentally swapped. Also available is lane arrival monitoring relative to an external synchronization signal. This allows to measure the propagation delay from the data through the link and also helps to identify potential sources of non-deterministic latency. If, for example, a single lane has a much larger latency than the other lanes, this might point to an issue with this particular lane. All monitoring is performed continuously. This allows to detect system failures in a short time span, which is, for example, useful in high reliability environments. Next, we will look at the gateway, or the HDL, that's provided as part of the framework. The gateway that is part of the framework provides all the HDL components that are necessary for JESD204 protocol handling. The framework follows the JESD204 standard and categorizes the components into 4 layers: the physical layer, the link layer, the transport, and the application layer. Each layer has their own specific function and interfaces between the layers are well defined. Components from each layer can be mixed and matched to implement a custom JESD204 transmitter or receiver chain. The physical layer takes care of the low-level protocol handling, turning ones and zeros into electrical signals or vice versa, also handling the parallel to serial and serial to parallel conversion, On the receiver side, it also performs clock recovery. The physical layer components are implemented using the high-speed transceivers that are built into the FPGA. At the link layer, there's a single component, the AD-IP JESD204. This is one of the central pieces of the framework and is responsible for the JESD204 protocol handling, which means it takes care of the control signals like sync and sysref. It is also responsible for aligning data from multiple lanes and for guaranteeing deterministic latency. At the transport layer, many different components can be found. These components handle converter-specific framing and deframing. This means they translate between the native sample data format and the format that is used to send the data over the JESD204 link. The transport layer components are often also capable of some light signal processing like IQ correction or test tone generation. At the interface to the application layer, the transport layer components produce or accept sample data in a standard format. The components at the application layer are not provided by the framework itself. This is where the user implements the application-specific logic, but the framework has a well-defined interface between the transport and the application layer for easy integration. At the software level, the framework provides drivers and associated system-level libraries which handle configuring the hardware and the gateway components. The software provides an API interface for configuring the converter and the JESD204 link. The API allows to specify configuration parameters as a logical value. This means that, for example, the sample rate is specified as a specific frequency, for example in Hertz, rather than a specific set of raw register values. Two different kinds of flavors of software drivers are available, Linux and NoOS, and which one should be used is influenced by application and environmental constraints. Using the Linux drivers means using the Linux operating system, which is a fully integrated and practice-proven operating system which has out-of-the-box support for many existing types of external peripherals which are outside of the scope of the JESD204 framework itself. In today's world of interconnected devices, it becomes more and more important to be able to interface with external systems. On the Linux side, the analog devices converter drivers use the industrial I/O framework. This is a standard framework for data converters, and it has many system-level auxiliary tools and libraries available. For example, integration into external tools like MATLAB Simulink, GNU Radio, or Visual Analog is available. The libio system library also has programming interfaces available for C, C++, C#, and Python. This allows developers to use the preferred environment and helps them to focus on the application they want to implement. The NoOS drivers, on the other hand, are more bare metal and have no additional external dependencies. This means they are suited for integration into other third-party operating systems or even applications that run without an operating system at all. This potentially allows to create very bespoke applications that can be fine-tuned to the target environment. For simple tasks, this might be easier to set up than in a fully integrated system like Linux, but the more external interaction is required, the more complex things get, and the more has to be done by hand. NoOS drivers are available as source code in the C programming language.
And now, back to Peter.
Thank you, Lars. Okay, now that we've covered what JESD204B is and why it's important, let's dive into the new development kit from Arrow. So, first of all, who is this kit made for? Who would use this kit? If you are designing a product that uses a large number of data converters running at high sample rates, say in the gigasample per second range, and are sending this information to an FPGA, this kit is for you. Examples include the applications I mentioned earlier: cellular communications, medical imaging, military applications such as radar, software-defined radio, secure communications, etc. Basically, anyone that is using ultra-high-speed data converters in their application should consider getting this kit. So the kit comes with the following components as pictured here. First, there's an ARIA-10 FPGA evaluation board, seen on the bottom of the picture. Then there's the Analog Devices DAC2 data converter board, which has the ADCs, the DACs, the clock, and power. And as pictured in the middle right, there's a power supply. There are two RF cables, which are used to loop the signal from the DACs back to the ADCs. And there's a gig Ethernet cable to connect to your PC. All of the licenses and the IP used are included with the kit at no charge for the first year. The software, firmware, and drivers needed to implement a complete solution are all included and can be downloaded from a GitHub site. Now I'm going to turn the presentation over to Robin to talk a little more in depth about the DAC2.
Thanks, Peter. Like Peter said, my name is Robin Getz. I'm going to be talking a little bit about the hardware. So the hardware that's included is the AD-FMC DAQ2-EBZ. So this is an FMC card that has three major components. One would be a high-speed ADC, or an analog-to-digital converter, known as the AD9680. The other would be the DAC, or the digital-to-analog converter, the AD9144. And then the clock chips, which can, like Lars was talking about, configure the clock rates, the JESD rates, the sample rates, which is the AD9523-1. So just a little bit about the clock chip. The clock chip has VCO frequencies from 2.9 to 3 gigahertz. That allows us to have output frequencies from basically 1 megahertz to 1 gigahertz, which allows us to drive the sample rates, sysrefs, all the other clocks that are necessary in the system. It has a frequency accuracy of less than a part per million, which is also determined by the VCXO accuracy. But on this board, it is less than 1 ppm. It does have zero delay operation, meaning that we can skew all the clocks. If we find, for example, the layout on the PCB, some of the lines were not length matched, we can actually adjust those in the clock chip itself. And although it does have, like Lars said, a Linux framework to go around with things and an OS framework, it also has an EEPROM inside the device that actually allows configuration settings to be stored and programmed in there so that during system boot operations they can run actually without any kind of software overhead. The other device is the digital to analog converter, the 9144. It's a quad 2.8 gigasample per second DAC. We don't actually use all 4 output channels on this board. We only use 2. It's 8 lanes of JESD204B, and it has a very low distortion design, a spurious free dynamic range of about 82 dB. It is a fixed latency, meaning it supports subclass 1, like Lars had talked about. It does have interpolation filters and a lot of other features. And this is about a watt and a half at 1.6 gigasamples per second. So it's a very, very high speed, low power for the speed kind of converter. The AD9680 analog to digital converter is a dual 14-bit device that operates up to 1.25 gigasamples per second. On this board, because of the clock chip, it's limited to a gigasample a second. It uses 4 lanes on JESD204, and it actually has 2 gigahertz of usable bandwidth. So you can actually sample into the 3rd and 4th microzone. It has about 95 dB of channel isolation, so it's very high performing, 80 dB of SFDR and 60 dB at 1 gigahertz of SNR. So it's an incredibly high performing device. The documentation can all be found on our wiki. So if you go to wiki.analog.com and just look for the AD-FMC DAC2-EBZ board, there will be all the schematics, the layouts, the board files, everything you would need to go to investigate how we designed the board and how you can design boards that would be similar to get you similar kinds of performance. And I'll pass things back to Peter to talk about a little bit more about the ARIA-10 device that it connects to.
Thanks, Robin. Okay, the ARIA-10GX FPGA development kit features the ARIA-10GX along with Max 5 and Max 2 CPLDs. In addition, there are power supply modules and ICs from both Intel and ADI on the board. Now, for this kit, Arrow has negotiated with Intel to include at no cost a 1-year license for Quartus Prime Pro Edition and DSP Builder software, as well as Intel's IP for the Neos 2 processor and the triple-speed Ethernet MAC. Here's a block diagram of the ARIA-10 as configured for the demo. Some of the features include it's built on a 20 nanometer process. There are up to 96 channels at 17.4 gigabits per second. Has the industry's only hard floating point digital signal processing blocks with speeds up to 1500 gigaflops. And it has the highest performance 2.4 gigabit per second DDR4 SDRAM memory and up to 12.5 gigabits per second for backplane support, which is the current standard for JESD204B. Here's a picture of the two boards together. Circular are known as the FPGA mezzanine card connectors, or FMC connectors, and these are how the two boards transport the signal back and forth between them. Now let's talk about the out-of-the-box experience, what you do, how you set it up, etc. As we mentioned before, there's a built-in demonstration which you actually download, and this showcases the 204B interface and the data converters and the FPGA talking to each other across the interface. The demo is very user-friendly. It's super easy to use. You do not even have to download the Quartus toolset to run the demo. Before we go into the setup, I just want to mention that the entire user guide is available on the GitHub site, which I will talk about a little more in a second. And so you don't have to remember these steps that I'm going to go through. I'm just going to go through them very briefly, just so you get a once-over and what's involved, kind of a preview. As I said, the hardware setup is pretty easy. Just attach the RF cables, as you can see there. Loop them together. What this does is this takes the signals from the DAC and feeds it back into the ADC. Normally, you might might want to transmit this wirelessly, but for this demonstration, we're just looping the signals right back. And do not use that FMC connector that's more towards the middle of the board. That has not been enabled for this particular demonstration. Here's the complete setup. You connect the Ethernet cable and the power, etc. And this is what it should look like. So now for to download the firmware and software as well as the documentation, you go to this Arrow GitHub site, and the address of that site is located here at the bottom of the slide. Using the pull-down menu on the left, once you get to that site, you select the latest branch revision, then click on the clone or download button on the right, and click download zip and save to your PC. Once you download the file and unzip it, you should see something that looks like this. Make sure to unzip the folder that's called Flash Files also. Now double-click on the executable file shown here for the IIO oscilloscope. It says ADI OS Master Setup. Double-click on that to install the application onto your PC. Now let's talk about running the demo. We're going to look at the signal path and the steps, some of the steps involved, look at the IIO oscilloscope application. We're going to see how to configure the inputs, view the outputs, as well as a few other inputs that you can use. Before we run the actual demo, let's take a look at what we are demonstrating. Here is a diagram showing the path the signal takes on the transmit side, going from the ARIA-10 FPGA to the AD9144 DAC, as illustrated by the dark blue arrow. First, the operator uses the analog device's IIO oscilloscope application to select a sine wave somewhere in the range between 10 and 500 megahertz. The ARIA-10 generates 2 copies of this frequency internally using its direct digital synthesizer block. These signals are phase shifted 90 degrees apart and will be the I, or in phase, and Q quadrature signals delivered to the DAC. These digital signals are then converted into the JESD204B format by the ARIA-10 in preparation for transmission. Next, the ARIA-10 sends the serialized digital signals across 4 lanes at a rate of 10 gigabits per second per lane to one of the FMC connectors on the ARIA-10 board. On the DAC2 board, the signals flow into its FMC connector across 4 lanes and is fed to the AD9144 DAC. The AD9144 converts the JESD204B formatted data into 2 analog signals using a sample rate of 1 gigasample per second and sends each out through SMA RF connectors to a pair of cables. Now we will look at the receive path as illustrated by the dark red arrow. Going from the right side of the figure to the left, the analog RF signals flowing through the 2 coax cables are fed back into the DAC2 board and sent to the AD9680 analog to digital converter. The 9680 samples a signal at a rate of 1 gigasamples per second, converts the analog back to digital, and formats into 4 JESD204B serial lanes. The data is then sent back along the 4 lanes at a rate of 10 gigabits per second per lane into FMC connectors and back to the ARIA-10 board. The ARIA-10 reconstructs the data from the JESD204B format back to parallel samples for processing. Using the ADI IIO oscilloscope application, the user can then view the captured data in the time and frequency domains. They can also download the data for post-processing using a tool such as MATLAB. To start the demo, just right-click on the batch file, jsddemo.bat, and choose Run as Administrator. The terminal window will open up with a sequence of instructions, some requiring user input. Again, all of this is outlined in the user guide, so you don't have to remember it. I'm just going through quickly to show you how it works. Once you've done this, the program will assign a temporary static IP to your PC. Then it will start a DHCP server and assign an IP address to the ARIA-10. Now we will launch the IIO oscilloscope application. We will use this to set the inputs generated by the ARIA-10 and to view the outputs on the return path from the ADC. In the Transmit 1 section, set DDS mode to 1 CW tone. And for this example, we will set the frequency to 40 megahertz and set the amplitude to -12 dB. The phase is irrelevant. Transmit 2 doesn't do anything on this particular setup, so you might want to set it to disable just to remind yourself. Now we just follow the instructions in the user guide to set up the channel triggering, select the input sources, and open plot windows. And we click Run to start. Here you will see a time domain plot, 2 waveforms, one for I and one for Q, 90 degrees out of phase with each other. The y-axis displays the amplitude of each signal. For this example, it goes between plus and minus 750 millivolts. You can view the results in the frequency domain as well. You should be able to see the fundamental frequency which you input as well as some harmonics. These are shown in the info box to the left. In this example, we see the fundamental of 40 megahertz, which we put in, as well as the 5th harmonic out at 200 megahertz. The frequency component that is visible at negative 40 megahertz is the image of the fundamental. One note is, if you want to reduce noise further, you can always increase the averaging from 10 to, say, 100, for example. If you want to observe the analog signals coming out of the DAC, using bench equipment, take the oscilloscope or frequency analyzer and connect the output of the DAC directly to the input of your test equipment. Here you can see that the output of the DAC, as viewed on the oscilloscope, is 40 megahertz, as we expect. The phase of the I and Q signals are also 90 degrees apart. You can also input more than one sine wave. Here I've put in 40 megahertz and 15 megahertz, and you can see it here in the time domain. And here it is in the frequency domain. There are a number of test signals that come preloaded with the IIO oscilloscope application, which you can access. Here is one example viewed in the time domain, and here it is in the frequency domain. Here's another example in the time domain and in the frequency domain. Now let's look at developing solutions using the kit. And for this, I'm going to hand over control to Stephen, who is our FPGA guru here at Arrow. So Stephen, you want to take this away?
Thanks, Peter. Hi, everyone. As Peter mentioned, my name is Stephen Kravatsky. I'm a principal application engineer at Arrow Electronics. In this next section, we will discuss the reference design that's available from Analog Devices, and we'll also discuss the IP and tools that are required to build it. ADI has extensive reference design support for FPGA-based products. These are hosted on the ADI Wiki site, and repositories for source code for these reference designs are hosted on the ADI GitHub site. 3 of the ADI GitHub sites relevant to this platform are the HDL GitHub, the Linux GitHub, and the IIO Oscilloscope GitHub. ADI provides user guides for the reference designs on its ADI Wiki website. Source code can be downloaded by the developer and used as a starting point for their custom designs. The developer's guide has been created for the Arrow high-speed data acquisition kit. This guide intends to provide a seamless initial out-of-box experience. It also navigates the user through the steps required to download the source for the reference designs and build them. The kit includes all the necessary tools and IP licenses required to build the reference design. The HDL reference design has been created using the QSYS and Quartus tools from Intel PSG. QSYS is a system design and integration tool. The reference designs are created in QSYS using IP blocks. They're automatically connected together using the Avalon or AXI interconnect standard. These tools can be driven from Tcl scripts or operated using a GUI flow. The preferred methodology for initially building is to use the Tcl script-driven flow, and this is because it's pretty hard to make any mistakes. It's a reproducible methodology, and you will get good quality results when you build for the first time. After that, if you're a more comfortable advanced user, you can then use GUI tools, but that's the recommended flow when you initially start it out. The embedded FPGA designs must use QSYS since it describes the embedded peripherals and the memory map that the user has created for the system. QSYS provides a library of existing IP components provided by Intel PSG and other IP vendors. Users can author their own IP in QSYS and publish it for reuse. In this instance, ADI have authored a number of pieces of IP, as was mentioned earlier in the presentation, that are used in this reference design. The QSYS integration tool saves significant time and effort in the FPGA design process. Quartus provides HDL tools for synthesizing Verilog or VHDL into gates. This QSYS snapshot shows the embedded portion of the reference design. Components have been selected from the standard IP library and use horizontal and vertical lines to represent their interconnects. Clocks and resets are wired from their sources to sinks on ports of all of the components. The processor portion is comprised of a Neos 2 soft RISC processor running Linux. It utilizes memory within the FPGA, M20K memory blocks as caches, and external DDR memory via the DDR memory controller as system memory. Slave ports of common peripherals such as the Ethernet MAC, the UARTs, PIOs, timers, and a SPI master are wired to the Neos 2 data master. In this section, we see the JESD204B transmit portion of the reference design from the ARIA 10 FPGA to the AD9144 DAC. The DAC sample data is extracted from DDR memory by the AXI DMA controller and passed to the Unpack IP block. The Unpack IP block supports a programmable number of channels. In this reference design, it is instantiated with 2 channels to support 2 of the 4 available DAC converters in the AD9144. The unpacked IP block unpacks the DAC data into two individual DAC channels and sends them to the AXI 809144 core. This core provides a transport layer to communicate the samples to the AXI JESD204B IP core. This core also provides a DDS dual-tone, PRBS, or pattern internal data sources. Finally, the AXI JESD204B IP core encodes the data using a soft 8B10B encoder and provides a link layer to the external 809144 DAC. This core utilizes Intel PSG transceiver IP for data transmission. Here we see the JESD204B receive portion of the reference design from the 809680 ADC to the ARIA 10 FPGA. It runs in the reverse order of the transmit path. ADC samples are received at the link layer by the AXI JESD204B receiver. They are decoded by the soft 8B10B decoder and then passed to the AXI 809680 IP core at the transport layer. The samples from the selected channel are then packed into a data stream and DMA'd into external DDR system memory. The 80 JESD204B IP core has the following features. Firstly, it's important to understand that the physical transceiver and the FPGA are duplex, each being a pair consisting of a receiver and transmitter. The ADI JESD204B IP core allows the designer to instantiate the core as a receive or transmit function. Software accesses these as independent, separately addressable cores. This IP makes use of the Intel PSG transceiver sharing feature. This allows independent transmit and receive IP cores to be packed into one physical transceiver core, as is shown in the script below. Now let's talk about the HDL IP cores. The ADI reference design is comprised of Intel PSG IP cores in the carrier-specific system, for example, the NEOS and the TSC Mac. Some of these require licenses. A one-year license for the following is provided with the kit: the Quartus Prime Pro software tools, which include QSYS, DSP Builder, which works in conjunction with MATLAB and Simulink, the NEOS 2 processor IP core, and the TSC Mac, or Triple Speed Ethernet Mac IP core. All ADI IP cores are fully open source and are publicly available on GitHub. The ADI JESD204B link layer IP is under the GPL license. All other IP cores, including the ADI JESD204B PHY, is under modified BSD license. The entire reference design is provided as open source under the BSD and GPL licenses. It is continually maintained across Intel PSG tool releases. Full documentation is provided on the ADI wiki site for building and customization. Embedded Linux runs on the NEOS 2 processor in this reference design. Linux is maintained and released in conjunction with the HDL source code. ADI provides a Linux GitHub repository for this. Kernel drivers for the ADI IP are specified and initialized by employing a device tree. The example snippet on the right of the slide shows a reference to the 809680 physical and link layer IP cores. The Linux Industrial I/O Framework, or IIO Framework, allows software to easily communicate with these ADC and DAC devices. It is registered under Linux as a device and can be accessed using standard Linux device nomenclatures. Now let's talk about DSP Builder. Hand-coded RTL must be written by RTL experts. The traditional RTL coding method is time-consuming and is prone to errors, which affects the design time taken to create a design. DSP Builder not only provides an abstracted, high-level design flow, but also provides a cookbook methodology to select parameters and great flexibility with changing specs for push-button RTL generation. It also offers a great level of flexibility in integrating algorithm development environment in MathWorks with Intel's FPGA design flow, allowing easy configuration of Intel FPGAs. The DSP sample rate in your design may exceed the FPGA clock rate, such as in a super sample rate system, for example, in high-speed wireless front-end designs. In a radar or direct RF system with gigahertz digital to analog converters, the signal driving the DAC can have a sample rate in the gigahertz range. This high-speed system requires innovative architectural solutions and support for high-speed parallel processing. DSP Builder Advanced Block Set Interpolation Filter IP has built-in support for super sample rate signals, and the vector support of its primitive library makes it easy for you to design your super sample rate module. DSP Builder connects Simulink to Intel FPGA development boards. This automatically creates a hardware verification system for DSP Builder designs. Users can easily create third-party board support packages for system-in-the-loop verification. This validates generated hardware compared to the original Simulink system model. Thanks, everybody. I'd now like to hand this back over to Robert.
Thanks a lot. So I'll just go over a little bit of where you can get help, where you can get some more information. On Analog Devices Engineer Zone at easy.analog.com, we definitely have people who can help out with questions, including myself and Lars, about the JESD cores or how to put them together in your system. And that, again, is easy.analog.com. There's a community there for FPGA. There's a community there for Linux. There's a community there for the no-OS kind of bare metal device drivers that Lars was talking about, as well as just basic chip support for high-speed DACs, high-speed ADCs, and clocks. There's also more information on our wiki page at wiki.analog.com. There, like I mentioned before, there will be all the schematics, all the documentation with the HDL, all the documentation with the JESD cores, and all the things like that that you may want to start looking at before you start asking questions, or we can just point you to the right places, because I know it's a little bit awkward to navigate sometimes. The JESD protocol, there's lots of information on Analog Devices Wiki. You can just go to wiki.analog.com/JESD204, and it'll take you to a lot of these different things. We do have a lot of other information on our website as well, including the JESD204B Survival's Guide, just at analog.com/JESD204. The IO oscilloscope that Peter talked about is also available from our wiki. It's just wiki.analog.com, and then just search for OSC or IIO oscilloscope. It'll take you to the right place. Again, that's Windows, Linux, Mac, totally cross-platform, and can communicate to remote devices or even run on a ARIA SoC platform directly on the ARMs.
Thank you, Robin. So, in summary, JESD204B is the interface to use when you're designing a system that requires multiple data converters, sampling at rates in the gigasample per second speed, and sending or receiving data to and from an FPGA. Arrow's high-speed data acquisition kit allows the systems architect to quickly develop and prototype a working solution. Arrow, Analog Devices, and Intel PSG offer a complete development environment. You get, for hardware, the ARIA 10 GX development kit and the Analog Devices AD-FMC DAC2 EBZ board. HDL sources is Verilog and open source, push-button Quartus Flow. Software sources is Linux and no OS open source. Documentation, it's not just a PDF, but there's an ongoing and evolving wiki. Actually, several wikis. There's support, there's FAQs, there's discussions, and collaboration from others, chiefly through Analog Devices Engineer Zone forum. You will be able to build the demo from sources as it is, rapidly prototype your design, customize your design to suit your needs, implement software-defined algorithms, and implement DSP blocks and algorithms in the FPGA. And again, to order this kit, simply go to arrow.com or contact your local Arrow sales representative. On behalf of all of us here at Arrow Electronics and Analog Devices, thank you for attending this webinar, and we look forward to working with you.
All right. Well, thank you, Peter. And now, before we begin with today's Q&A, please fill out the feedback form that's opened up on your computer. If your pop-up blockers have prevented the form from launching on your computer, You can click on the red survey icon at the bottom of your screen. And to complete the form, please press the Submit Answer button at the bottom of the page. Thank you in advance for filling out the feedback form. Your participation in this survey allows us to better serve you. We're now going to move on to the question and answer portion of our event. As a reminder, to participate in our Q&A session, just type your question into the text box located to the right of the presentation window, or click on the Q&A icon at the bottom of your screen, and then click the Submit button. Please note that we're going to try to get to as many questions as we can in the time that we have left, but if we're not able to get to your question today, someone will be getting back to you via email after the program is over. So with that, let's go ahead and move on with our first question. Looks like our first question is going to be, with which version of Quartus Pro is the reference design compatible? And this one, I believe, is for Steve. Steve? Or Stephen?
Hi, thank you. So the latest stable version that's released out there is 16.1. So that's the tool that it is compatible with. And the next stable version will be the 17.0 version of the tools. Thanks.
All right. Thank you, Steve. We're going to move on to our next question here for you. How do you save the raw data fed to the IIO oscilloscope application?
Okay, yeah, this is Peter. What you do is from the IIO oscilloscope app, you choose File, then Save, and select the output data option you want.
All right, thank you, Peter. We'll move on to our next question here, and one moment here. The next one here is, what do I have to do in order to start developing with the kit besides installing Quartus?
So this is Stephen. So hi. So what I would recommend is just go to Google and just Google GitHub space arrow-SOC-FPGA. That'll take you to the Arrow main GitHub page. And then once you're on that page, look for the Arrow High-Speed Data Acquisition Kit link. It's the one at the top. When you click on that, it'll bring you to the entry page. And in the README section, just look at the README. It's got a description on getting started. And really what you need to do there, we've got two sections. One is steps 1 through 5 for initial out-of-box experience. In other words, bringing up the kit and running the demo. And then the second set of instructions, 6 and 7, are used to rebuild the reference designs. But really what we referenced in there is the user guide. So just click on the link. It'll bring up a PDF that you can download, and then just follow those steps, and you'll be good to go.
All right, thank you. Our next question here, it says, can I use ADI's JESD HDL IP, or can ADI's JES HDL IP be used in an ASIC?
Yeah, I'll take that one. This is Robin Getz. So I would say that there's nothing excluding you from using it in an ASIC. It's been verified and validated on a variety of FPGA tools. It has not been verified or validated on what we would consider an ASIC flow, so you may have to do some work on that. For more details, you probably want to just contact Analog Devices at JESD204-licensing@analog.com, which is just a quick email address to check things out. So.
All right, thank you, Robin. Next question here for you. It says, I want to ask a question about the ARIA 10GX FMCS. As I know, there are two HPC FMC connectors on a 10GX. So can we use both FMCS for the DAC2 board? And for example, can we connect two DAC2s boards on an A10GX board? And can we use them directly with no problem?
Hi, this is Lars. So the reference design that we provide has been specifically designed for one DAQ2 board, and it has to be connected to the first FMC header. But both FMC headers, as you said, are HPC headers, so they can support an DAQ2 board. And if you are going to replicate basically the logic, the current logic that's in design basically instantiates everything twice, you can also use two DAQ2 boards on the single A10GX. All
right, thank you, Lars. And we'll move on to our next question here. looks like our next one is going to be, when will the Aero high-speed data acquisition kit be available, and what is the cost? And that's for Peter.
Oh, thank you. So the kit is available now, and the cost is $6,000, and that includes all the Quartus Prime software, DSP Builder, tool licenses, the IP for the Neos 2 processor and the triple speed Ethernet MAC, analog devices, JESD204B IP, and all that. That covers licensing and everything for the first year.
All right, thank you, Peter. And it looks like we have one more question here. Just as a reminder to our audience to ask a question, just type your question into the Q&A text area, and then click the submit button, and we'll try to get to as many as we can here with the time that we have left. Looks like we might be able to sneak in one or two, so if you're really quick with typing in your question, we'll get right to it. Okay, our last one that we have here, how can I order the kit or obtain more information?
Okay, this is Peter again. Yes, the best way to do that is to send an email to aero_HSDAK, which stands for High Speed Data Acquisition Kit, at aero.com. So aero_HSDAK at aero.com.
All right, thank you, Peter. And just as a reminder to our audience, we had a question here that asked if they could get a copy of the slide presentation. All of that is available in the resource folder at the bottom of your screen. And that looks like all the questions that we have for today. So on behalf of Peter, Stephen, Robin, Lars, and Paul, we'd like to thank you for participating in our Q&A session. So thank you, gentlemen. And for more information related to today's webinar, please visit any of the resource links available in the green folder icon at the bottom of your screen. Within the next 24 hours, you'll receive a personalized follow-up email with details and a link to today's presentation on demand. Once again, we'd like to thank you for attending today's webinar, High-Speed Data Acquisition Using Analog Devices DAQ2 or DAQ2 and Intel's ARIA 10, brought to you by Tech Online, Aero, and Analog Devices. This webinar is copyright 2017 by Aspen Core. The presentation materials are owned by our copyright by Tech Online, Aero, and Analog Devices, and the individual speakers are solely responsible for their content and opinions. On behalf of our guests, Aero and Analog Devices, I'm Chris Keach. We'd like to thank you for joining us, and we hope you have a great day.